Quantum technology stands at the forefront of scientific innovation, promising to reshape our world in ways that were once the realm of science fiction. Rooted in the principles of quantum mechanics, a branch of physics that explores the behavior of matter and energy at the smallest scales, quantum technology harnesses phenomena that defy our everyday experiences. At the heart of this revolution are concepts like superposition, entanglement, and tunneling, which allow quantum systems to perform tasks far beyond the capabilities of classical counterparts. The journey from the abstract mathematics of quantum theory to practical devices has been long and complex, but recent decades have seen rapid progress, with quantum computers, sensors, and communication networks moving from laboratory curiosities to functioning prototypes and, in some cases, commercial products. To appreciate the transformative potential of quantum technology, it is essential to understand its foundational principles. Quantum mechanics emerged in the early 20th century as physicists grappled with phenomena that classical physics could not explain. Max Planck's solution to blackbody radiation, Albert Einstein's explanation of the photoelectric effect, and Niels Bohr's model of the hydrogen atom all revealed that energy and matter behave in discrete packets, quanta, at microscopic scales. Erwin Schrödinger and Werner Heisenberg formalized these ideas into a coherent mathematical framework, introducing the wave function and the uncertainty principle. Unlike classical objects, which have definite properties, quantum systems can exist in multiple states simultaneously, a phenomenon known as superposition. Furthermore, particles can become entangled, meaning their states are linked regardless of distance, leading to correlations that challenge our notions of causality and locality. These counterintuitive features are not just theoretical curiosities, they underpin the new generation of quantum technologies. Quantum computers, for example, exploit superposition and entanglement to perform computations in ways fundamentally different from classical machines. While a classical bit can be either 0 or 1, a quantum bit, or qubit, can be both at once, vastly expanding the computational space. Algorithms designed for quantum computers, such as Shor's algorithm for factoring large numbers, demonstrate exponential speedups over their classical equivalents, potentially rendering current cryptographic systems obsolete. This has profound implications for cybersecurity, prompting the development of quantum-resistant encryption methods and spurring interest in quantum key distribution, which leverages the no-cloning theorem and the disturbance caused by measurement to guarantee secure communication. The physical realization of qubits is a major technical challenge, driving research into various platforms. Superconducting circuits, trapped ions, semiconductor quantum dots, and topological qubits each offer distinct advantages and complications. Superconducting qubits, used by companies like IBM and Google, rely on circuits cooled to near absolute zero, where electrical resistance vanishes and quantum effects dominate. Trapped ion systems, favored by IonQ and Honeywell, use electromagnetic fields to isolate and manipulate individual atoms. Each approach must contend with decoherence, the tendency of quantum systems to lose their fragile quantum properties through interaction with the environment. Error correction and fault tolerance are therefore central concerns, requiring intricate schemes to detect and mitigate errors without collapsing the quantum state. Beyond computation, quantum technology is revolutionizing sensing and measurement. Quantum sensors exploit the extreme sensitivity of quantum states to external influences, enabling unprecedented precision in detecting time, gravity, magnetic fields, and other quantities. Atomic clocks, the most accurate timekeeping devices ever built, rely on transitions between quantum energy levels and now underpin global positioning systems and telecommunications networks. Quantum gravimeters and magnetometers promise breakthroughs in geology, navigation, and even medical imaging, detecting minute variations that would be invisible to classical instruments. The ability to measure with quantum-limited precision opens new frontiers in fundamental physics, such as searching for gravitational waves, dark matter, or testing the limits of general relativity. Quantum communication, meanwhile, offers the promise of unbreakable security and new paradigms for information transfer. Quantum key distribution, QKD, protocols, most notably BB84, use the fact that any attempt to eavesdrop on a quantum channel inevitably disturbs the system, revealing the presence of an intruder. Early demonstrations of QKD over optical fibers and free space links have led to commercial products and even satellite-based networks, as exemplified by China's Mihius satellite. The vision of a global quantum internet linking quantum processors and sensors across continents is taking shape, though significant technical hurdles remain. Entanglement distribution over long distances, quantum repeaters, and integration with existing infrastructure are active areas of research. The impact of quantum technology extends far beyond physics or computer science. In chemistry and materials science, quantum computers could simulate molecules and reactions with unparalleled accuracy, unlocking new drugs, catalysts, and materials. Classical computers struggle to model the quantum interactions of even modestly sized molecules, but quantum algorithms can efficiently capture the complexity of electronic structures. This capability could accelerate the discovery of high-temperature superconductors, advanced batteries, or novel pharmaceuticals, transforming industries from energy to healthcare. In optimization and logistics, quantum algorithms hold the potential to solve problems that are intractable for classical systems. Many real-world challenges, from routing delivery trucks to managing financial portfolios, involve searching vast spaces for optimal solutions. Quantum annealers, such as those developed by D-Wave, are already being tested for these applications, though their true quantum advantage remains a subject of debate. As more powerful and error-corrected quantum computers come online, their impact on business, transportation, and supply chains could be profound. The promise of quantum technology also raises important questions about ethics, security, and societal impact. The prospect of breaking current encryption schemes threatens the privacy and integrity of digital communications, while the concentration of quantum expertise and resources in a few countries or corporations could exacerbate global inequalities. Ensuring that the benefits of quantum advances are widely shared and that risks are managed responsibly will require international cooperation, robust policy frameworks, and ongoing public engagement. Education and workforce development are critical to realizing the quantum future. The interdisciplinary nature of quantum technology demands expertise in physics, engineering, computer science, and mathematics, as well as new skills in quantum programming and hardware design. Universities and governments are launching initiatives to train the next generation of quantum scientists, while private companies are developing user-friendly software platforms and cloud-based access to quantum processors. Building a diverse and inclusive quantum workforce will be essential to fostering innovation and ensuring that the technology serves the broadest possible range of interests. Government investment and strategic planning play a pivotal role in advancing quantum technology. Recognizing its economic and national security significance, countries around the world have launched ambitious quantum initiatives. The United States National Quantum Initiative Act, the European Union's quantum flagship, and China's multi-billion-dollar investments reflect a global race to establish leadership in this emerging field. Public funding supports basic research, infrastructure, and collaboration between academia and industry, while regulatory frameworks seek to balance innovation with security and ethical considerations. Industry engagement is accelerating the transition from laboratory research to real-world applications. Tech giants like Google, IBM, Microsoft, and Amazon are investing heavily in quantum computing, offering cloud-based quantum services, and partnering with startups to explore use cases. A vibrant ecosystem of quantum startups is tackling challenges ranging from hardware development to software tools, error correction, and application-specific solutions. Venture capital and corporate investment are fueling rapid progress, but the path to widespread commercial adoption remains uncertain, with technical, economic, and market hurdles to overcome. Standardization and interoperability are emerging as key issues as quantum technologies mature. Ensuring that different quantum devices, protocols, and software platforms can work together seamlessly will be crucial for building scalable systems and fostering a competitive marketplace. International organizations such as the International Telecommunication Union, ITU, and the Institute of Electrical and Electronics Engineers, IEE, are beginning to develop standards for quantum communication, cryptography, and computing, laying the groundwork for a robust global infrastructure. Public understanding and acceptance of quantum technology will shape its trajectory. The abstract and counterintuitive nature of quantum mechanics can make the field seem inaccessible or mysterious, but effective science communication and education can demystify the concepts and highlight their practical relevance. Outreach programs, interactive exhibits, and accessible online resources are helping to build awareness and excitement, inspiring students and citizens to engage with the quantum revolution. Looking ahead, the future of quantum technology is both exhilarating and uncertain. Fundamental breakthroughs in materials, device architectures, and error correction could unlock new capabilities and accelerate progress. The integration of quantum devices with classical systems, so-called quantum classical hybrid computing, may provide practical benefits even before fully fault-tolerant quantum computers are realized. Advances in photonics, cryogenics, and nanofabrication will continue to push the boundaries of what is possible, opening new avenues for research and application. At the same time, the quantum era will pose novel challenges. The transition from prototype to production-scale systems will require overcoming formidable engineering and manufacturing obstacles, ensuring the security and resilience of quantum networks, protecting against new forms of cyber attack, and safeguarding sensitive information will demand constant vigilance and innovation. Ethical considerations, including the potential for job displacement, surveillance, or misuse of powerful new capabilities, must be addressed proactively. International collaboration and competition will shape the pace and direction of quantum innovation. While the race for quantum supremacy captures headlines, cooperation on standards, research, and best practices can maximize the benefits and minimize the risks. Forums for dialogue among scientists, policymakers, industry leaders, and civil society will be essential for navigating the complex landscape of quantum technology and ensuring that it serves the common good. In conclusion, quantum technology represents a paradigm shift with far-reaching implications for science, industry, and society. By harnessing the strange and powerful laws of the quantum world, we are poised to unlock new realms of computation, communication, and measurement, transforming the way we live, work, and understand the universe. Realizing this potential will require sustained investment, interdisciplinary collaboration, and a commitment to ethical and inclusive innovation. As we stand on the threshold of the quantum age, the choices we make today will shape the trajectory of technology and humanity for generations to come.